Okay, welcome back. We're on 8.3 Laws of Logarithms. So we're going to step through each of these main three laws. And then we're going to do lots of examples on how these laws can be applied for rearranging logarithmic expressions and equations. Product law of logarithms. Log base c of m times n equals log base c of m plus log base c of n. It's like you can separate the two of them, okay? Here's the proof. Let log base c of m equals x and log base c of n equals y, where m and n and c are positive real numbers and c is not equal to 1. Write the equations in the exponential form. So if m equals c of x and n equals c of y, right? So we're changing these into exponential form. Well, m times n equals c to the x times c to the y. We know from our product law of exponents, and see the relation here, m times n equals c to the x plus y. Okay, turn this into logarithmic form. Okay, the base becomes the base of the logarithm. Okay, the exponent is the result. Okay, and then the argument is the new argument in the logarithm. So I have log base c of m n equals x plus y. Okay, and then 4. Log base c of m times n equals log base c of m plus log base c of n. So I'm doing this. X equals this. So I'm yeah, sorry. I'm substituting. Okay, I gotta read this here. Okay, from this step, what does x equal? Well, x equals log base c of m. Well, what does y equal? It equals log base c of n. I substitute it back in and we get our product law. Quotient law, log base c of m divided by n equals log base c of m minus log base c of n. Okay, proof, let log base c of m equals x, log base c of n equals y, where m, n, and c are positive real numbers and c does not equal 1. Write the equations in the exponential form as, similar to the previous example, where m equals c to the x and n equals c to the y. Okay, m divided by n is c to the x divided by c to the y. Okay, we're just substituting here. M divided by n, I'm using my quotient law for exponents. See the relation? Quotient law. Okay, quotient law for exponents. And then I'm changing it into logarithmic form. The base becomes the base of the logarithm. Okay, the exponent becomes the exponent here. And then the argument is still the argument. Okay, so we're putting the logarithmic form. And then the last step here is the substitution step. We're going to unsubstitute or backward substitute. Here's the x, here's the x, here's the y, here's the y. Put it back in. I have log base c of m divided by n equals log base c of m minus log base c of n. That's the quotient law. The power law. Log base c of m raised to exponent p equals p times log base c of m. Let log base c of m equals x and log base c of n equals y, where m and c are positive real numbers, c does not equal 1, and p is a real number. Write the equation in exponential form as m equals c to the x. M equals c to the x. Let's raise both sides to exponent p. So I get m to the p equals c to the xp. Let's put it into logarithmic form. Okay, so I have the base as the base, so I'm going to take this as my power. So I take the base of the c becomes the base of the logarithm. Okay, right there. Okay, the exponent becomes the result in the logarithm, and then the argument is the argument in the logarithm. Let's do a little bit of rearranging and simplifying. Actually, substitute right here. Oops. Okay, so what are we doing? Sorry about that, folks. X. Let's substitute back in log base c of m. So I get log base c of m raised to the exponent p equals log base c of m times p. The p I'm going to write as a coefficient in the front, p log of log base c of m equals log base c of m raised to that same exponent p. Tip: before combining logarithms with the same base, using the product or quotient laws, all log terms need to have a coefficient of plus or minus -1, making it necessary to first apply the power law in many circumstances. Okay? Let's do a lot of examples to illustrate this. Next page. Okay, using the laws of logarithms, you will use the log laws to simplify expressions into a single term or to expand expressions. You need to understand the log laws in both directions. So log base 6 of x divided by y, I'm going to use the quotient law. So that is log base 6 of x minus log base 6 of y. Letter B, quotient law again. Log base 3 of 9 minus log base 3 of the cube root of x squared. Okay, let's go further here. What's log base 3 of 9? Well, that's just 2. 2 minus, let's do something here. I don't want to leave it like this. We want to put it in simplest form. So this is log base 3 of x, x squared. Oh, goodness. Hang on a second. Sorry, folks. Start over. 2 minus log base 3 of x to the 2/3. So when I'm converting from a radical to an exponent, that's what it looks like. Okay, I'm going to, for this one, I'm going to apply the power law. Okay, so I'm going to bring the 2/3 as an exponent out in front as a coefficient. So it's 2/3 log base 3 of x. Next one, log base 5 of square root of x times y. Oh, let's see. Let's let's convert this to instead of a radical, I want to write it with exponents like this. Okay. First thing I can see is that this is an exponent, so I can apply the power law. So power law says the exponent becomes a coefficient out in front, 1/2 log base 5 of xy. Okay, keep going. I see a product law inside the parentheses, so it's 1/2, and then put a giant parentheses there. Two things we're going to write, log base 5 of x plus log base 5 of y. So that x and y can be separated using the power law. Sorry, this one is the product law. This one was the power law. Okay, and then just distribute 1/2 log base 5 of x plus 1/2 log base 5 of y. Okay, next one. Let's ramp up the complexity here. Log base 7 of x to the 5th times y divided by square root of z. Let's start writing it. I have a product law on the numerator, and then the z in the denominator allows us to use the quotient law. So if I do this in one step, so log base 7 of x to the 5th plus log base 7 of y minus, well, quotient law applied to the denominator, log base 7 of z to the 1/2. I'm going to put a set of brackets around there, okay, just to know that it's minus that entire term. If you had two terms in the denominator, then you would use a set of brackets with that minus out in front. Let's get into the good practice or habit of doing it, even if it's just one term or two terms or three terms, okay? Each of these, this first one, I'm going to apply the power law. So the 5 exponent comes out in front as a coefficient. So 5 log base 7 of x plus log base 7 of y minus, well, there's just one term, so I'm going to drop the brackets. This 1/2 exponent comes out in front, and that becomes log base 7. Oops. Log base 7 of z. Okay, and that's the simplest form. Determine, example 2, determine each expression as a single logarithm in simplest form. So now we're going to use the quotient, product, and power law to work backwards and make a single logarithmic expression. Okay, I want positive exponents, no radicals. Okay, let's go. So I have log base 2 of 4x cubed times y to the 4th minus log base 2 of 20x to the 5th y plus log base 2 of 10x y to the 6th. Okay, first thing I see here is, let me rearrange it like this. So log base 2 of 4x cubed y to the 4th plus log base 2 of 10x y to the 6th minus log base 2 of 20x to the 5th y. I do it this way because I want to show where I'm applying the product law and the quotient law. So the product law is to the first two expressions. So log base 2, okay, in giant brackets, log base 2, and then in giant brackets, the first two terms, 4x cubed y to the 4th times 10xy to the 6th divided by the last term, 20x to the 5th y. Okay, and then the last part is, let's simplify everything. So that's log base 2 of, in the numerator I have 4 times 10 is 40 divided by 20 is 2 in the numerator. I have x to the 3rd and x, that's x to the 4th, but there's an x to the 5th in the denominator, so I'm going to put an x in the bottom using my quotient law for exponents. Y to the 4th and y to the 6th is y to the 10th divided by y to the 1st. That's y to the 9th in the numerator. Okay, so my resulting single logarithmic expression is log base 2 of, in brackets, 2y to the 9th divided by x. Okay, next one. Log base 6 of x to the 6th plus 3/4 log base 6 of x to the 4th minus log base 6 of square root of 16x. Okay, first off, what would I do here? I'm going to, so I have the two first terms, first two expressions are added together, so that's going to be my product law, and then subtracted by the last logarithmic expression. That's the application of the quotient law. Let me change all these radicals. Let's see. Let me change all these radicals into exponents, and then I'm going to change this, applying the product law, sorry, the power law backwards. So log base 6, what do I have here? Log base 6 of x to the 6th plus, so this is what I'm doing, log base 6 of x to the 4th to the 3/4. So I'm applying the power law backwards, minus log base 6 of 16x to the 1/2. Okay, let's do a little bit of simplification before we combine terms here. Log base 6, well, x to the 4th raised to the 3/4 exponent, that is just x to the 3rd, minus log base 6 of 16x to the 1/2 is 4x to the 1/2. Okay, now that we got everything simplified, let's now apply the product law with the quotient law. So all in one giant logarithmic expression. One thing to pause here and note is that, notice I have the same base. If I don't have the same base, I can't do this application of product law, quotient law, to put everything together. Okay, just a brief pause there to mention that. Okay, let's combine everything together. So I have x to the 6th, so I'm applying the product law to the first two terms, x to the 6th times x to the 3rd, divided by, okay, quotient law, 4x to the 1/2. Okay, let's simplify. Log base 6 of x to the 9th divided by 4x to the 1/2. Okay, I want positive exponents, no radicals. Log base 6, goodness, log base 6 of x to the 9th is x to the 18 halves divided by 4x to the 1/2. log base 6 of x to the 18 halves divided by x to the 1 half is x to the 17 halves divided by 4. Okay, and we're done with that one. Next page, folks. Example 3. If log base 5 of x equals 2, then determine log base 5 of 125x. Log base 5 of x equals 2. Okay. I can change this to exponential form, right? So I know that 25 equals x. Okay. Let's keep that off to the side. Determine log base 5 of 125x. Well, what the heck does this have to do with log laws? Well, let me do this. Remember, we can do this with our product law. Okay, log base 5 of 125 plus log base 5 of x. Well, what is this? 5 to the third equals 125, so I can evaluate this logarithm as, what? 3 plus, let's plug in for x here, log base 5 of, we said x is 25. Okay, 3 plus, well, what's log base 5 of 25? 5 raised to what exponent gives you 25? That is 2. So 3 plus 2 is 5. Next one, letter B. If log of 5 equals a and log of 4 equals b, determine an algebraic expression in terms of a and b for each of the following. Okay. Let's see. Log of 25. So let me use the quotient law. Log of 25 minus log of 64. Let's rewrite this like this. These are both perfect squares, folks. So I'm going to write it as log base 5 exponent 2 minus log base 4 exponent. Oh, let's do 4 because it's asking for that 4 there. Okay, log base 4 exponent 3. Use our power law. 2 log of 5 minus 3 log of 4. This is A, this is B, A and B. So I'm going to rewrite it as 2A minus 3B. Okay, that's all we're doing. Next one, log base 4 square root of 5 divided by 125. Let's break it up with our quotient law. Log of 4 square root of 5 minus, quotient law. Yep, log of 125. Okay, this one I can break it up further. Log of 4 plus log of square root of 5, right? Because we're multiplying 4 times square root of 5, we can break it up using our product law, minus log of, let's rewrite it as log of 5 cubed. Couple more things. Log of 4, right? We already have log of 4. That's great. I'm trying to get these to look like log of 5 so I can make the substitution. Log of 5 to the, well, square root, we can say log of 5 to the 1/2 minus log of 5 cubed. Let's make the appropriate substitutions. We want to rewrite this in terms of a and b. Okay, log of 4 is b plus log of 5 to the 1/2. Oh, before we do the substitution, folks, sorry, folks, we're not done yet. 1/2 log of 5. I'm going to apply the power law. Here, I got to apply the power law. Log of 5, 3 times log of 5. Now I can make the substitution. Log of 4 is b plus 1/2 log of 5 is a minus 3 times log of 5 is a. And we're done. Oh, no, we're not. b plus 1/2 a minus 6/2 a. I need to simplify. Sorry about that, folks. That is b minus 5/2 a. Example 4. Let's keep going. Use the laws of logarithms to simplify each expression to a single logarithm, then state the value of each expression. So log base 3 of 9 plus log base 3 of square root of 3. This we can evaluate right away. That is just 2 plus, let's do this, log base 3 of 3 to the 1/2. Okay, 2 plus, let's keep going. Let's power law, right? 1/2 log base 3 of 3. 2 plus 1/2. Well, 3 log base 3 of 3, that is just 1. So it's 2 plus 1/2. And that's 5/2. Okay. Oh, the other way. Okay. So if we're applying the laws of logs, here's the other way. Or, okay, I'll show you another way. We can do it this way, but it's making you use laws of logs. Okay, so we want to do that. So we're adding two logarithmic expressions with the same base. So I have log base 3 of log base 3 of 9 times square root of 3. Let's do a little bit of rearrangement in the bracket. So log base 3 of 3 squared times 3 to the 1/2. I'm just rewriting it in terms of exponents. So that's log base 3 of 3 to the 5/2. Okay, I'm going to use the power law. Bring that 5/2 forward here as the coefficient times log base 3 of 3. What's the last step? What's log base 3 of 3? That is 1. So it's 5/2 times 1, and that equals 5/2. Well, it's the same as that we had before. Okay. Next one, log base 5 of 1,000 minus log base 5 of 4 minus log base 5 of 2. Let me do this first, right? I'm going to group it like this. Okay, let's worry about this one later. That's log base 5 of 1,000 divided by 4. I have the same base. I can apply the quotient law, and it's minus log base 5 of 2. That log base 5 of 2, let me just let me do this. Leave it there for now. I'm going to simplify. Log base 5 of 1,000 divided by 4 is 250 minus log base 5 of 2. Okay. Same base. I'm subtracting here, right? I'm going to apply the quotient law again. So log base 5 of 250 divided by 2. That's log base 5 of 125. Okay, and then let's think about log base 5 of 5 cubed. You can go straight to say, log base 5 of 125, that's 3, right? But let's just show the application of as many laws of logarithms as possible. Just humor me here. This exponent 3, power law, 3 log base 5 of 5. 3 times log base 5 of 5 is 1, so result is 3. Another example, folks. 2 log base 3 of 6 minus 1/2 log base 3 of 64 plus log base 3 of 2. Okay, we need to put all this together. Okay, so first one, I'm going to apply the power law. Log base 3 of 6 squared minus log base 3 of 64 to the 1/2 exponent plus log base 3 of 2. Let's do this. Log base 3 of 36 minus log base 3 of 8 plus log base 3 of 2. So I want to make this as simplified as possible before I do all my product and quotient law. Okay, so let's think about it this way. I'm not going to rearrange this, but I want you to see that log base 3 of 2, this one, and log base 3 of 36, that one, we're adding those two and we're subtracting log base 3 of 8. So when I combine it all in one, log base 3 of 36 times 2, right, because those are the two expressions I'm adding, divided by 8. because I'm subtracting log base 3 of 8. Again, I have the same base in all three logarithmic expressions, so I'm applying product and quotient law all in one. Simplified, log base 3 of, let's see, that's 72 divided by 8, that's 9. Let's evaluate this logarithmic expression, log base 3 of 9. 3 to what exponent equals 9? Well, that is 2. Next page. Example 5. Simplify each expression to a single logarithm in a reduced form. State the restrictions on the variable. Okay, we know from our transformations lesson, we know from our basics of logarithms, our intro, all those restrictions. So we have to come back and remember what are the possible restrictions, okay? 4 log of base 3 of x minus 1/2 log base 3 of x plus 5 log base 3 of x. Okay, let's simplify and reduce. So I'm going to apply the power law. So I'm going to make that an exponent 4 minus 1/2. Inside the bracket, let's apply the product law. So that's log base 3 of, oh shoot, sorry. Let me do this. I didn't see that, so I got to do this step. Log base 3 of x plus log base 3 of x to the 5th. I got to apply the power law inside the brackets as well. So let's keep going. Now let's combine using the product law. Okay, so that's log base 3 of x times x to the 5th. Log base 3 of x to the 4th minus 1/2 log base 3 of x to the 6th. Okay, log base 3 of x to the 4th minus log base 3 of x to the 6th to the 1/2. So I'm applying the power law. Okay, let me bring it up here. Log base 3 of x to the 4th minus log base 3 of x cubed. So just a little bit of simplification there. Let's apply the quotient law. Log base 3 of x to the 4th divided by x to the 3rd. And I have log base 3 of x. Okay, what's my restriction? Okay, from here, right, I have a denominator in the x. It's kind of like asking what are the restrictions on a rational function. You have to always think about the denominator, right? X must be greater than 0. Okay, remember also if it's negative, it'll why is x greater than 0, right? First of all, x cannot be 0 because I can't have it a 0 in the denominator. That's undefined. Why can't x be negative? Because if I have x as negative, that makes the argument negative. And if the argument's negative, a logarithmic expression, there's no possible answer, right? So just be careful of that. So x needs to be greater than 0. Okay, letter B, next one. Okay, just ramping up the complexity here. Log base 2 of x squared minus 9 minus log base 2 of x squared minus x minus 6. Okay, this one, same base. I'm going to apply the quotient law. Log base 2 of x squared minus 9 divided by x squared minus x minus 6. Oh, that's a rational expression as the argument, right? We're going to have to factor that, right? X minus 3, x plus 3. That's x minus 3, x plus 2. Okay. X minus 3 divided by x minus 3 is 1, so I'm left with log base 2 of x plus 3 divided by x plus 2. Okay, that's as far as we can go. We want to combine it to one single logarithm. What are my restrictions? Okay, remember from rational expressions, right? I can't pull all my restrictions from here, right? Because that's the simplified form. I have to look at every single step and see where I can possibly have a denominator of 0, right? So my restrictions, folks, I'm going to look here because it's the factored form of here. So x cannot equal 3, right? Otherwise, you'll have a denominator of 0, and x cannot equal negative 2, right here. Otherwise, you'll have a denominator of 0, okay? Also, let's see, x must be greater than 0, okay? Again, why? Because we can't have a negative argument. Otherwise, the logarithm doesn't calculate. It doesn't work, right? So let's take this. This, when I have x is greater than 0, right? This will not be a restriction that's necessary because I already have x is greater than 0. 0 is greater than negative 2, so we need not write this one, okay? This x does not equal 3, right? We can say this. So x does not equal 3, but x is greater than 0, okay? But let's think about this. So if x does not equal 3, but x is greater than 0, what if I pick 2? If I put 2 here, that's going to make the argument negative. So I also have to say x is greater than 3. Okay? So if I say x is greater than 3, then I don't need to say this, and I don't need to say this either, and this is your only restriction. Okay? So these restrictions come in layers, right? So you have to think about the restrictions because now we're talking about logarithms, right? You have that added complexity of the argument can't be negative. Okay, so you have to think about that as well as the denominator that can't be negative. All right, folks, almost done here. Okay, connecting laws of logs to transformation. So you can obtain the graph of g of x equals log base 3 of 9x by applying either a translation or a stretch to the graph of f of x equals log base 3 of x. Well, how does that work? Describe the stretch that could be transformed from f to g. Well, let's write g of x equals log base 3 of 9x. If I line it up to my general transform, sorry about that, folks, that's 9x. If I line it up like this, log base x equals log base 3 of bx, well, we know from our general transformation model for logarithms that the b represents, the b is related to or represents something about a stretch factor, a horizontal stretch factor, right? But let's be careful. So b equals 9. The factor of the stretch is 1 over absolute value of b, so that's 1 over absolute value of 9, and therefore the factor is 1/9. So I will say this is a horizontal stretch about the y-axis by a factor of 1/9. Okay, describe the translation that can transform f to g. So how the heck do we get a translation? Okay, and these two graphs are the same. G of x, in this case, we're going to show it as a translation. Well, how does that happen? G of x equals log base 3 of 9x. G of x equals, well, let's apply the product law, log base 3 of 9 plus log base 3 of x. G of x equals, what's log base 3 of 9, folks? That is 2. Plus log base 3 of x. Okay, let me just rewrite it with the log as the lead term. So g of x equals log base 3 of x plus 2. And let me write underneath the general transformation model, log base 3 of x plus k. Okay, now do you see where the translation's coming in? What does k equal? K equals 2. What does that mean? That's a vertical translation 2 units up.